Okay, in this lecture, we turn to the study of finite volume methods for scalar nonlinear conservation laws, building on the theory of finite volume methods for the scalar advection equation and linear systems, but now incorporating nonlinear problems where we know we can have shock waves and rarefaction waves coming out of the Riemann solution. But we can still look at defining Godunov's method in various ways, similar to what we did for the linear case. And we'll look at sort of how different formulations based on fluxes or cell averages or wave propagation relate to each other. And because they're rarefaction waves, there's some new issues that come up. And one big issue is the question of transonic rarefaction waves, which we'll look at in some detail, and then look at how we can do a wave propagation form of Godunov's method that can be viewed as an approximate Riemann solver along with what's called an entropy fix in the case of transonic rarefaction waves. So recall Godunov's method for any conservation law. We can look at defining Godunov's method by taking piecewise constant initial data at time tn, so t goes upwards here, and then based on that piecewise constant data, we define Riemann problems at every grid interface. If we can solve those Riemann problems and construct a solution at time tn plus 1, then we can average that solution to get a new approximation at the next time, and then we can repeat the process, view that as a piecewise constant function at the next time that defines a new set of Riemann problems. And we've seen that for linear problems, the Riemann problem consists of a set of waves that are just jumps in the solution moving at some speeds, eigenvalues and eigenvectors of the coefficient matrix in the linear case. In the nonlinear case, though, things get a little more complicated because the waves could be shock waves or rarefaction waves, and rarefaction waves, since they spread out, they have a more complicated structure, and so it may not be clear how to generalize these ideas. And if you recall, we looked at sort of three different ways of defining Godunov's method. One is what I just described, of compute the new cell average by integrating over the cell at time tn plus 1. And if the solution of the Riemann problem involved a rarefaction wave, then the exact solution at time tn plus 1 would be a little more complicated. It wouldn't be just piecewise constant. It would have a rarefaction part of it. And so computing that integral might seem more complicated, but in principle, we could do that. But a much easier way to look at it for the scalar nonlinear case is to think of it in terms of computing the values at the interfaces and then the flux at the interface, and then using the integral form of the conservation law to say that the new cell average is the old cell average as modified by the flux at the two edges of the cell integrated in time. And because the solution of a Riemann problem is always a similarity solution, even for nonlinear problems, the solution along those dashed lines in this figure at the cell interfaces, the solution is constant in time over short enough time that the waves don't travel more than one grid cell, which is true provided the Courant number is less than 1. And so if we can compute the Riemann solution, then all we really need is the value along that one ray, and that allows us to compute the flux at the right boundary and the left boundary of that cell, and then this formula gives a way to update the cell average based on that. So for a scalar problem, that's an easier way to think about it, certainly, than the first form, where we might have to integrate a rarefaction wave in space. And it also avoids the problem of having to think about how do we generalize the idea of wave propagation to rarefaction waves rather than just jumps. However, when we expand this to systems of equations, nonlinear systems of equations, or to higher order methods, looking at something more like a Lax-Wendroff method and then applying limiters to get a high resolution method, it turns out that the idea of having a wave that's propagating at some speed is still very useful in both of those situations. So we'll also look at how we can sort of rewrite Godunov's method for a scalar and nonlinear problem as in the form that we looked at as this sort of wave propagation form, where we looked at updating the cell average by what I called, I think, the fluctuations arising from the left edge of the cell and from the right edge of the cell, which are sort of the net effect of all the waves that are coming in from one side or the other that are affecting the cell average. And this allows us to use the waves, these WPs, that are calculated from the Riemann solution together with the speeds in this first order Godunov update, and then we can also use those waves and speeds in adding on second order correction terms. And for a nonlinear system, we can hope to split up the jump in Q as a set of waves, one for each family. But we still have to deal with the issue that how do we handle a rarefaction wave and how do we get that to fit into this framework. But before we tackle that, let's look at Godunov's method in the flux differencing form in a little bit more detail. So this is, again, the basic idea we've seen before, that if we can define this q tilde n, a function that starts out being piecewise constant at time tn and then evolves as the exact solution of the differential equation, and then since that's a similarity solution, it's constant along this line between cell I-1 and cell I, and that's the value we called q Riemann, which is a function of the two cell averages on either side. And if we can calculate that from our Riemann solution, just that one value out of the whole Riemann solution, then we can define an interface flux f by integrating the flux evaluated at that value over time. But since it's constant in time, that once we divide by delta t to get an average in time, that simply reduces to the flux evaluated at that one value. So all we need out of the Riemann solution is that one value in order to calculate the fluxes at the edges of the cells. So again, if we have a similarity solution as the solution of our Riemann problem, then we can always do that. And in particular for a convex flux, for example, Berger's equation, a quadratic, or traffic flow, a different quadratic, we know that the Riemann solution always consists of only a single wave, either a shock wave if the characteristic speed is increasing as you go from left to right, or a rarefaction wave if the characteristic speed, first case is if the characteristic speed is decreasing as you go from left to right, but a rarefaction wave if the characteristic speed is increasing so that characteristics are spreading out. So in the convex case, there's always only a single wave, but it might be a rarefaction wave rather than simply a discontinuity. So if we look at the Riemann problem with a scalar convex flux, and in that case, f prime of q is monotonically increasing or decreasing, and if you think about what the Riemann solution can look like, there's really 6 possible cases. 5 of them are drawn here. We'll talk about the 6th one in a moment. But the cases that we see here, we either have a shock wave that's moving to the left, or a rarefaction wave that's moving entirely to the left, or we can have a shock wave moving to the right, or a rarefaction wave moving entirely to the right, or we can have this interesting case in the middle here, where we have the characteristic speed on the left is negative and the characteristic speed on the right is positive, and so the rarefaction wave spreads across the discontinuity. And that's the case that's called a transonic rarefaction, where the characteristic speed is negative to the left and positive to the right. And if it's a convex flux function f, then there can be at most one point where f prime of q is equal to 0, since f prime is monotonically increasing or decreasing. And that point, call it qs, where f prime of qs is equal to 0, that point is called a sonic point, or a stagnation point sometimes. But the terminology sonic point comes from gas dynamics, because in gas dynamics we know that the wave speeds are u plus or minus c, where u is the fluid velocity and c is the sound speed. And we've often thought about that in terms of u being 0 in linearized acoustics, or typically we think of u as being smaller than c, subsonic flow. But you can also have cases where u is larger than c in magnitude, which is supersonic flow. And in that case, you can have both of these characteristic speeds having the same sign. But there's also this sort of transition point where the fluid velocity is exactly equal to the sound speed in magnitude. And that's the transonic, or the sonic point, where the flow is going from subsonic to supersonic, or vice versa. So those are the sonic points in the problem. Oh, and the 6th case that I didn't draw here is the case where the shock is moving at speed 0. And notice that in that case, f of ql has to equal f of qr, because the Rankine-Hugoniot condition involves f of qr minus f of ql divided by the jump in q. So if that speed is 0, then the two fluxes are the same. And notice in this picture that if we're thinking about trying to compute the flux at the interface to use in our flux differencing formula, in these two cases, the flux at the interface is just going to be f at the right state, because the interface lies in the right state as time goes forward. And in these two cases over here, the flux at the interface is just going to be f in the left state. And in this case down here, if the shock is moving at speed 0, then those two are the same, so you could choose either one and it doesn't matter. But the more interesting case is this case in the middle here, in which case the flux is the flux at the sonic point qs, because that's the value that lies along the characteristic f prime equals 0, which is the characteristic that moves right along this interface as time advances. So the fact that f prime of qs equals 0 means that q is identically equal to qs on that characteristic. So for a convex scalar problem, if we look at solving the Riemann problem and then try to compute the flux along the interface, or along the line x equals 0 in this picture, there's really only 3 possible values that the flux can take, these 3 values written up here at the top. So for the case, the formulas are slightly different if f double prime is negative everywhere, but in the case where f double prime is positive everywhere, then these are the formulas for the flux at the interface. Again, it's always in terms of cell averages now. If we're computing a flux at the interface between two cells, it's always either the flux in the cell on the right, or the flux in the cell on the left, or the flux at the sonic point, if the sonic point sort of lies in the middle of a rarefaction wave between the left and right state. And here this S that comes in here is just the Rankine-Hugoniot shock speed. You have to think about this a bit maybe to see why those are the right formulas. But it turns out there's another form of this solution that's more general, and not only does it work both for f double prime positive everywhere, it also works for f double prime negative everywhere, but moreover it works for any flux function, even non-convex flux functions. And that is to say that the flux at the interface is simply the minimum of f of q anywhere between qi minus 1 and qi. And if qi minus 1 is less than or equal to qi, it's a minimum over that interval. But if qi is greater, or qi minus 1 is greater than or equal to qi, then it's a maximum over that interval instead. So maybe it helps to draw a picture for Berger's equation where the flux is just a quadratic like this. If you have a left state and a right state that are these 2 points, for example, then if you think about it, if this is q left, qi minus 1 in the formula, and this is q on the right, then in that case the characteristic speed and the shock speed is to the right, and if it were a rarefaction wave, all the as it would be here, because the characteristic speed is increasing, all of the characteristic speeds are positive. So the flux at the interface, or in this case here, and the flux at the interface is just f of ql, which is the minimum value of f over this interval. Similarly, if we switch those states, then if, say, this is q left and this is qr, we're looking at the same interval, but we'd be looking at this case where, in this case, qr, which is qi, is less than or equal to qi minus 1, so we look at the maximum value of f of q. That's f of ql in this case. This is the case where we have a shock wave moving to the right. The Rankine-Hugoniot speed is positive, the slope of the chord there. And again, this flux at the interface is f of ql. And in a situation where we have a transonic rarefaction wave, that would be a case where we have the 2 states on either side of the sonic point, and we would have to have, let's see, the q right on the right, q left on the left so that the characteristic speed is spreading out, and we have this sort of picture. And so we'd be in this situation, and so we'd look at the minimum value of f over the interval, and that would then give us exactly the sonic point down here at the middle, or f evaluated at the sonic point would be the value of the flux in that case. So this general formula, you can convince yourself, works fine for any convex problem, but it turns out it even works for sort of arbitrary non-convex fluxes as well. Okay, so this formulation gives us a way to look at the Godunov, or look at Godunov's method as a flux differencing method. But again, if we want to sort of extend this to higher order methods, we'd like to be able to add in correction waves. And so I'm going to try to rewrite this in more like the form that we used of this wave propagation algorithm. And again, the form that we started with there for the first order method was to write it in this fluctuation form rather than a flux differencing form, where the A plus delta Q at the left edge, that sort of represents the net contribution of all the waves that are moving to the right from the left edge. So it's waves from the left edge, but only the ones for which the speed is positive. So the positive part of lambda p, remember, is 0 if lambda p is negative. And so this is just summing up speed times the wave over the positive waves. And similarly, the A minus delta Q is a similar sum, but using the negative part of each eigenvalue. So we're only summing up the waves that are moving to the left, and they're coming from, well, I wrote the formulas here in terms of I minus a half, but what we actually use is A minus delta Q at I plus a half, so it's the waves that are coming from the right edge of the cell. So it would be the same formula, but with I incremented by 1. And in the case of a linear system, we saw that another way to write this, if we sort of create a matrix A plus by diagonalizing A and then zeroing out the negative eigenvalues and then recombining R times lambda plus times R inverse, that gave us a matrix A plus, and this script A plus delta Q minus a half was exactly equal to this matrix A plus multiplied by delta Q, the jump in Q. And similarly, A minus delta Q I minus a half, we could interpret as, or compute as being the matrix A minus times the jump in Q. But for nonlinear problems, it's a little more complicated than just looking at the matrix, because the Jacobian matrix is changing everywhere, and solving the Riemann problem is more complicated, but we'll see that we can often still come up with waves and speeds. And so in the nonlinear system case, when we get to that, we'll look at this A plus delta Q and A minus delta Q as being combinations of waves and speeds, but it's no longer interpreted as any particular matrix times the jump in Q. And so these symbols, this A minus delta Q, I minus a half, and A plus delta Q, I minus a half, with the script A, that should be viewed as just a symbol meaning the left-going or right-going fluctuations. And then the way we use those fluctuations is in the formula at the top. And in the case of scalar advection, it's the same, but there's only a single wave, m is equal to 1. So the only wave is the full jump in Q, or just Qi minus 1. And the corresponding speed is the same everywhere. If it's constant coefficient advection, it's just the value u. And then these fluctuations, A minus and A plus, turn out to be the same wave, but multiplied either by u minus and u plus. And if u is just a scalar value, then one of these is always 0. If u is positive, then u minus is 0. If u is negative, then u plus is 0. So one of these fluctuation vanishes, and the only contribution to the cell average is coming from the side that's on the upwind side. So let's go back to this flux differencing formula now and ask, can we sort of manipulate this into the form that also looks like this fluctuation form? And it turns out you can. If you have any flux differencing formula, like the one at the top here, however we determine these fluxes Fi plus a half and Fi minus a half at the interfaces, we can rewrite it in terms of fluctuations, A plus delta Q and A minus delta Q, by defining them as at the bottom here. So all you have to do is define A minus delta Q to be the difference between the interface flux, whatever you've calculated in your flux differencing formula, minus the flux in cell I minus 1, the cell on the left of the interface. And the A plus delta Q similarly is the flux in the cell on the right minus the flux at the interface that came out of your flux differencing formula. And in the case of a linear system, you can show that this definition of A minus delta Q and A plus delta Q based on fluxes that come out of solving the Riemann problem and looking at the solution along the interfaces agrees exactly with the sort of wave propagation form on the previous slide of computing these fluctuations as sums of wave speeds times waves over the waves going in each direction. So the upshot is the wave propagation algorithm that implements Godunov's method. If we want to implement exactly Godunov's method that comes out of the flux differencing formula, we can just do what's done at the top here. We can rewrite the flux differencing method as this sort of fluctuation approach by defining the fluctuations in terms of the interface fluxes that way. But for a high resolution method, we also want to add in correction terms that are going to be defined in a way that's similar to the scalar advection and linear system case. And for that, we need a wave W and a speed S, as we'll see. And when we get to nonlinear systems, for each characteristic family, we'll need a wave and a speed that we can use in the high order correction terms and apply limiters to, and so on. And it turns out that in order to generalize Godunov's method to something more like Lax-Wendroff with a limiter added, we can define the waves to be just the jump in Q, as you would expect, and we can define the corresponding speeds using the Rankine-Hugoniot jump condition. So that's this expression at the top here. The jump in F divided by the jump in Q is the speed at which the discontinuity between cells I minus 1 and I would move, assuming it's a shock wave. In the special case for Qi minus 1 equals Qi, that denominator would vanish, and so in that case you could say that we should really look at the limiting case of the Rankine-Hugoniot speed, which is the characteristic speed as Qi minus 1 approaches Qi. Although in this case, where the two states are equal, it doesn't really matter how you define it, because in that case this wave would be 0 if Qi equals Qi minus 1, so it doesn't really matter how you define the speed in terms of the second order correction terms. They'll vanish in any case, but just for consistency, that would be a natural way to define it. So another way to look at this is that we've defined approximate Riemann solver that isn't really the correct Riemann solution in all cases, but that fits nicely into this waveform. Once we've defined these waves and speeds down here at the bottom, this is actually the speed at which a discontinuity would propagate if the solution is a shock wave. If it's a rarefaction wave, then things should really be spreading out, but this is maybe the best we can do in terms of defining a single wave and speed, even in the rarefaction wave case. And so you can think of this as defining an approximate Riemann solver. It's correct for a shock wave, but it's only an approximation for a rarefaction wave, an approximation in which we're replacing the true rarefaction wave with a discontinuity that still satisfies the conservation law because the Rankine-Hugoniot condition is satisfied, but doesn't satisfy the entropy condition, or wouldn't be the admissible solution that we're really looking for. So in that sense, it's only an approximate Riemann solution. But we can define it by using this fluctuation form at the top here, and then going back to our original definition of these fluctuations based on the speed, positive or negative part of the speed, times the wave. So forget about the flux that came out of Godunov's method. Instead, just use the waves that are the full jump in Q in this case for each wave, and the speeds that are the Rankine-Hugoniot conditions. And for scalar advection, if the speeds are all just equal to U, that's exactly the right thing to do, and that is Godunov's method. But for nonlinear problems, we can now think about using the same formulas, but with this Rankine-Hugoniot speed. And again, this would in fact give us the exact solution of the Riemann problem if it's a shock wave, but it's only an approximate solution if it's a rarefaction wave. Approximate in the sense that we're not modeling the rarefaction wave, we replaced it with a shock. But it turns out that if you use this in an updating formula, and then you are averaging the solution onto the grid cell, as we do in Godunov's method, then after you average things, this approximation is also exact for the rarefaction case after we average things. And we'll look at that in more detail on the next couple slides. But in general, even though it seems like only an approximation, it turns out it gives you the right answer, except in the case of a transonic rarefaction, where things are a little more complicated, as we might expect, because that's the only case where the interface flux is more complicated than just being the flux to the left or the right. So let's suppose that we have some initial data for Berger's equation. So these are cell averages. So this is the Q values that are increasing here, and this being Berger's equation with f prime of u equals u, the characteristic speeds would be increasing, so these would all turn into rarefaction waves. And if we assume that these values are all positive, so 0 is down here somewhere, then the evolution would be that all of these waves move to the right as rarefaction waves that stay entirely in the cell to the right. And so we have this picture, if we sort of looked in the xt plane now, that from each interface we have a rarefaction wave that's spreading out to the right. And notice the rightmost characteristic speed of this rarefaction wave would have to be equal to the leftmost characteristic speed of this one, and that would be the value in the cell in between for Berger's equation. So we have this sort of picture, and then that gives rise to the solution shown above at the end of a time step. But now at the end of the time step, what do we do with this? Well, we average it over the grid cells, and we compute some new cell averages, some values in here. Well, once we've done that averaging, we've kind of thrown away all of the structure of this rarefaction wave. And so the idea in this kind of approximate Riemann solver is, if instead of propagating these waves as rarefaction waves, if instead we propagated them as discontinuities traveling at the Rankine-Hugoniot speeds, then those would be the waves that are shown in red here. So we'd be looking at taking this initial data, and rather than putting a rarefaction wave, just put a shock that's moving to these points. And because we choose the shock speed to be the Rankine-Hugoniot speed, that's still a weak solution of the conservation law. It still conserves mass. And so if we look at that compared to the proper rarefaction wave solution that's shown in blue there, we see that the cell average within each cell is going to be exactly the same. So once we compute a cell average based on these shocks that we propagated, even though the shock wasn't the right solution locally, once we've done the averaging, it doesn't really matter whether we used rarefaction waves or shocks. And the averaging, sort of another way to think about it, the averaging adds in some numerical viscosity that smears out these shocks and gives us in the end something that's more like a rarefaction wave. But the place where you run into problems with this is if we have a transonic case. So now let's suppose this is Q equals 0 is here somewhere, so that we have some jumps that are spreading out to the left as rarefaction waves, and other jumps are spreading out to the right. And this jump in the middle here is partly spreading to the left and partly spreading to the right, so that as time advances, whoops, going the wrong way, time advances, it spreads out like this. Or the picture in terms of the Riemann fans in the xt plane, we have the expansion fan there, and here we have an expansion fan that's a transonic rarefaction wave. Okay, well now you can see that if we were to replace that solution with the solution that consists of discontinuities propagating at the Rankine-Hugoniot speeds, then we don't get the right thing after we average, because in this cell to the right here, for example, the red curve is entirely equal to this value. So its cell average is still exactly where it was at the beginning of the time step, whereas the true cell average, if we calculated the correct rarefaction wave and then average that, would have to be a little bit lower. And similarly in this cell, the exact solution is probably a little bit higher than what comes from this shock wave, which in this case is just barely moving to the left because the 0 point isn't exactly centered there. If it was exactly centered, then this discontinuity wouldn't move at all, and you'd have a discontinuity that just sort of persists in your initial data. But you can see that in general, trying to use discontinuities propagating at the Rankine-Hugoniot speeds are not going to give us the right solution locally around here. You might still hope that as you refine the grid, things get better, but that's not going to be the case, as we'll see in some computational examples. Before showing the computational examples, let me mention then what we sort of have to do to fix this up. And it's something that's often called an entropy fix. And in the next lecture, I'll talk more about entropy conditions and where this terminology comes from. But again, the basic idea is that the weak solution isn't always unique. And in particular, if you have a discontinuity in your initial data that should spread out as a rarefaction wave, you could get instead a discontinuity that satisfies the Rankine-Hugoniot condition but doesn't spread out the way it should, and that would be an entropy violating discontinuity for reasons we'll talk about later, where that terminology comes from. But the idea is that we want to make sure that the solution we're computing is approximating the physically correct solution. So in the case of these convex scalar problems that we're looking at, the fix is to kind of abandon this idea of using the wave and the speed in these first order fluctuation form of our flux differencing and go back to the sort of flux differencing form. So instead of using the wave and the speed for these first order terms, we'll go back to using the true flux at the interface, which is F evaluated at the sonic point, and define the fluctuations as flux differences between that value F at the sonic point, which is the value of the flux right along the interface, and the fluxes in the neighboring cells. So go back to using the flux differencing form of Godunov's method in this particular case of a sonic rarefaction wave. And it turns out if you do that and otherwise use this formulation, that's sufficient because this formulation, the wave propagation formulation, really reduces to the flux differencing formula everywhere except in the case of a transonic rarefaction, at least for the scalar nonlinear problem. Things can get a little more complicated in the systems case. But for the scalar problem, you can do this. So you might ask, why don't we just always use the sort of the flux differencing form? Well, again, it's nice to have these waves defined in terms of the higher order correction terms that we'll look at adding in a moment. But that's the basic idea of this entropy fix. So let me switch now to a few examples. So this is a notebook. I'm not going to show you all of the code, but I wrote a little function that just makes an animation for different Riemann problem data. And so I can specify where the initial discontinuity should be here at x equals 0.2, and what the left and the right states are, and which method I want to use, and whether or not I want to include this entropy fix. So let's first look at this upwind method, just written in this wave propagation form without any entropy fix, so ignoring the possibility of transonic rarefactions, and see what happens. And here I've taken data to start out with that's positive everywhere, so and it also is a shock wave rather than a rarefaction wave, so it doesn't matter whether we use the entropy fix or not here. And what happens as this propagates, it spreads out a little bit, as you'd expect. Upwind method is fairly diffusive, but it propagates basically in the right way. And in fact, if you look at this, go back to the beginning, although it smears out a bit, and this discontinuity is kind of smeared over a couple of intermediate grid cells, it never really smears out more than that. And if you remember when we looked at the advection equation with the upwind method, it tended to get more and more smeared as time goes on. That's because we could think of the numerical method, the upwind method, as modeling an advection diffusion equation where there's a diffusive term that's smearing out this interface in addition to the advection term that's simply moving everything at constant speed. And in the advection diffusion case, the characteristics for the advection part are parallels. So when the things get smeared out, they stay smeared out. There's nothing to sharpen them back up. But here with Berger's equation, which is what I'm solving here, you end up sort of modeling a viscous version of Berger's equation where you have a viscous term on the right-hand side, but you still have the nonlinearity of Berger's equation. So when things get smeared out, Berger's equation is trying to sharpen them back up in this situation. And so the natural sharpening of the nonlinearity sort of fights against the smearing that's introduced by the first-order upwind method. And so you actually typically get sharper discontinuities for a nonlinear problem than you might expect if you've only been looking at solutions of linear problems. Let's see, I also, in this code, I implemented extrapolation boundary conditions so that when things hit the boundary, they should simply move out of the domain with no reflections. And those boundary conditions are very good numerical boundary conditions for one-dimensional problems. You typically get no sort of spurious waves coming back in. Okay, so for a simple shock, it looks pretty good. This next problem is similar, but now with a rarefaction wave situation. So the state on the left is less than the state on the right, but still they're both positive, so it's not a transonic case yet. And now the true solution should spread out as a linear function in between because the flux is quadratic. And we see that upwind with this fairly coarse grid is definitely showing some smearing here at the corners, but it's basically approximating the right solution. And if we refine the grid by a factor of 2, we'd expect the errors near these kinks to probably go down by a factor of 2 or so. So it looks fine, and again, it propagates fine out of the boundary with these extrapolation boundary conditions. Okay, but now let's look at the transonic rarefaction case. So if we go from q equals minus 0.5 to plus 1.5, and so characteristics are moving at speed minus a half on the left and plus 1.5 on the right. And now what happens is kind of interesting. It should be a rarefaction wave. It should be this transonic rarefaction wave shown in red. And we get part of that rarefaction wave okay, but then there's a jump discontinuity here that never moves. And if you notice, this is jumping from minus 0.5 to plus 0.5. And with the flux of Berger's equation, f of minus 0.5 is equal to f of plus 0.5. So the Rankine-Hugoniot condition says that's a jump discontinuity that can move at speed 0. And that's exactly what we see. And without putting in this entropy fix, we're in exactly the situation we were looking at a couple slides ago where things do not spread out properly. So that's what happens there. And you might hope that if you refine the grid, it might look better, but it won't. If you put in twice as many points, it'll look pretty much exactly the same. So here's the same thing, but with the entropy fix set to true, which means that when we detect the transonic rarefaction wave, we'll actually use the proper Godunov flux. Still the first order upwind method otherwise. And so there's some smearing near the corners, but at least it's approximating the right thing. Now there's still a little glitch here. In fact, technical term, it's often called the entropy glitch that shows up right at the sonic point when you use a method like this. It's a little steeper there than it should be, and that's because when you think about what's going on with Godunov's method, when you have this transonic rarefaction wave, it's spreading partly into the cell on the left and partly into the cell on the right, and it doesn't really get enough into either cell to affect the cell averages the way that neighbors are being affected. Turns out once we add in higher order correction terms, you can get rid of this pretty well, but there's a little bit of an artifact in the upwind method, even with the entropy fix turned on. So this is really just Godunov's method for Berger's equation. We're using the exact solution of the shock and rarefaction everywhere, including at this transonic rarefaction. Also, this jump here is of order delta x, and as we refine the grid, it would get smaller, and so it does in fact converge. It just doesn't look as nice as it might. Yeah, so then we can look next at what happens when we try to extend this to higher order methods. So if we go back here, and I'm not going to say too much about this now, but the basic idea is we can extend things in exactly the same way we did for the scalar advection equation. So we start with Godunov's method, which we can think of writing in this form, where these fluctuations either come from the approximate Riemann solver of just using waves and speeds, or maybe have the entropy fix added in which case it's the exact fluctuations that come from flux differencing. And then we can extend that method to a Lax-Wendroff type method. I put Lax-Wendroff in quotes because for the advection equation, this gives you exactly the Lax-Wendroff method. But in the nonlinear case where the speeds are varying from one grid cell to the next, there are several different variations of how Lax-Wendroff method might be defined. In the book, there's also a two-step Lax-Wendroff method that's defined. But this is one variation that's still second order accurate if things are smooth enough. And the idea is that we start with the first order fluctuation form, but then we add in a correction term. And the correction term, as we did in the linear case, we look at it as a flux difference, where the fluxes are these correction fluxes, F tildes, that are defined from the next term in the Taylor series expansion to give the second order accuracy. And the generalization of what we looked at before is this formula here. For the case of scalar advection, the speeds S were simply the advection velocity U. And in both cases, this wave W is just the jump in Q from one cell to its neighbor. So this is exactly the same thing we looked at for the advection equation, but with the uniform constant speed U replaced by the speed at each interface that's given by the Rankine-Hugoniot condition. That's really the only difference between this scalar advection and this case. Well, we may also have a sort of this entropy fix added in as well, but that would be a second difference. So if we want to make this a high resolution method, because again, Lax-Wendroff will give us problems with oscillations, then the idea, just as for the linear case, is that we replace this wave, which was in the scalar case, just the full jump from one cell to the next, we replace it by a limited version W tilde. And the W tilde wave in the scalar case, at least, can be defined in exactly the same way it was for advection, where we derived these high resolution limiter methods. In other words, the correction wave is the original wave modified by some factor phi of theta, where the theta is a ratio of the wave coming out of the Riemann problem in the upwind side. So this capital I, remember, was I minus 1 if the speed is positive, or I plus 1 if the speed is negative. But looking at the wave on the upwind side and comparing it to the wave that we're trying to limit, that ratio is close to 1 if things are smooth, in which case this limiter function phi of theta was also close to 1. But if there's a big jump or a big difference between the wave that we're trying to limit and the neighboring upwind wave, then we might apply any of the limiters we looked at before, the min-mod limiter, the monotonized-centered, the Van Leer limiter. Any of them can be applied in exactly the same way. It's the same function. So we'll look more at this when we talk about nonlinear systems, where things get a little more complicated because the waves then become vectors rather than just scalars. But at least in the scalar case, it's a very direct generalization of the advection algorithm. And if we go back over here to the computations, so Lax-Wendroff without any limiters, in the case of, for example, just a rarefaction wave where everything is positive, so it's not transonic. What do we get in this case? Well, it spreads out like it should, but it also develops oscillations, just as we saw in the linear case, if we just use what I called the Lax-Wendroff formula. But if we use something like the min-mod limiter on top of the Lax-Wendroff formulation, so apply that to limit each wave based on the wave in the upwind direction, then we get a solution that looks much better. And it not only matches the true rarefaction way pretty well, but it has better accuracy around these kinks than the upwind method did. But finally, let's take a look at the transonic rarefaction case. So this is the same problem we looked at before, but now with the min-mod method. And to start with, without any entropy fix, just to see whether sort of adding in these second order corrections alone is enough to fix up our entropy violating shock that showed up in the other solution. And what we find is that with the min-mod limiter anyway, it's not enough. We still get a jump here. It's slightly smaller than what just upwind gave, where it jumped from minus 0.5 to 0.5. Here it's jumping from more like minus 0.4 to 0.4. It's still symmetric about 0, so that it has 0 shock speed. But it still gives a discontinuity here that doesn't vanish as you refine the grid. But it turns out for these limiter methods, it depends a bit on what limiter you use. So there's a figure in the book where instead of min-mod, I showed what happens with the monotonized centered limiter, again without the entropy fix. And in that case, it looks a little better. Well, quite a bit better actually, because there's no discontinuity that persists here, although it's still not matching the transonic rarefaction as well as we might like. But if you use one of these limiter methods, either one of them together with the entropy fix, so that we avoid this problem of the entropy violating discontinuity persisting at the origin, then that also gets rid of the sort of entropy glitch that we saw with just the first order method, even with the entropy fix turned on. And so here now at the sonic point, things are looking nice and smooth. There's not even a jump of size delta x. Things look very nice in this case. So the upshot is that by using both the high order correction terms with appropriate limiters and the entropy fix to make sure that we're using the correct first order flux, we can get very nice results. And this carries over, as we'll see, also to nonlinear systems of equations. So just to summarize, here's the picture that's in the book. And Godunov's method with no entropy fix, in the transonic case, you get this big jump that persists. If you add the entropy fix, then you can still have a smaller jump that's ordered delta x that persists. If you look at a high resolution method without the entropy fix, and here it was the monotonized centered, so it didn't have any discontinuities, but it still wasn't looking very accurate. But if you do the high resolution with the entropy fix, then things look pretty good. So we'll go on and look at extending these methods to nonlinear problems later.